Hi students, and welcome to Lecture 5 of the Allen 2016A Electronics 1 course. I'm your lecturer for today, Mohammed Dango, and we'll be looking at types of diodes. Kicking off, we'll be looking at the solar cell and the photodiode, followed by the LED or light emitting diode. Then we're going to look at the Schottky barrier diode, and finally the Zener diode. Now, students, refer to your textbook, Chapter 1, pages 48 and 53, if you need to have any clarification on this lecture. And remember, anything said or done in this lecture can and will probably be used as a question in the test or exam. So, students, a solar cell, you probably know that they're found on solar panels. Now, how exactly do these solar cells work? Did you know that they were actually diodes? Well, now you do. So looking at this very beautiful picture that I've drawn, we have the sun, which creates the photons, and the photons then land on the depletion region of our solar cell, which is basically a PN type diode that has been doped. So in the depletion region, you know that it sets up an electric field, and when the photons then hit onto this electric field, we see some stuff happening. So looking into the next slide, when the photons hit onto the depletion region, they create what is known as the photoelectric effect. So the photons bombard the depletion region and they hit into the covalent bonds that are here, and they impart energy to the free charge carriers within the depletion region. So once they impart this energy to the free charge carriers, if we then connect a resistor to our solar cell, what we see happening is all these free charge carriers that are generated within the depletion region due to collisions from photons that are coming from the sun. These free charge carriers can then flow according to the electric field. As you know, the holes will flow in the same direction as the electric field, and the free electrons will flow in the opposite direction of the electric field. And this generates a current, IPH for I photon current, which can then go through some sort of a load. Here we represent it using a resistor, and you can see the voltage across that resistor. So important to note, students, that a solar cell is basically a diode that can then be used as a source to generate a current, IPH, and it generates this current because photons that are coming from the sun hit into the depletion region of the diode, impart energy into the depletion region. This energy causes the generation of electron-hole pairs, and these electron-hole pairs then start flowing, and that is how we have this current IPH. Now, students, a very similar diode to the solar cell is the photodiode. Similar in the sense that, yes, we have the sun, the photons, and the photoelectric effect. But what the difference here is that a photodiode is a reverse biased diode. Now remember, the solar cell was a diode that was connected to a resistor or a load, and it was the solar cell that generated the current to supply that. Here we have a source that is reverse biasing our photodiode. And a photodiode, the reason why we use them is to detect the amount of light that is available. So how does it go about doing that? Well, because our photodiode has been reverse biased, we know that the electric field that is created within this depletion region is going to have quite a wide width, because the electric field will be comprised of the depletion region original electric field added to the electric field from the reverse biasing source. So when the photons now bombard our depletion region, once again, very similarly to the solar cell, they impart energy into the depletion region. This energy then generates electron-hole pairs or free charge carriers, and these free charge carriers are then able to flow. Electrons in the opposite direction of the electric fields, holes in the same direction of the electric field, and that generates this current IPH. That, students, is a solar cell and a photodiode. This is what the circuit schematic of these two components looks like. Remember that. And next, students, we have the light emitting diode or LED. And all in LED is a simply forward biased diode. You guys are very familiar with forward bias in a diode. When a diode is forward biased, then we know that the electric field that is set up within the depletion region gets narrower, and the electric field within the diode is now replaced by the electric field generated by the source that is forward biasing our diode. And when this electric field is present and our diode is forward biased, we know that our free charge carriers, such as electrons, they then flow in the opposite direction of the electric field, whereas our holes flow in the same direction, and that creates this current, which we see flowing in our forward biased LED. But now, how does an LED then actually emit light? So we know it's forward biased, but how does it actually emit light? Well, let's first consider a silicone lattice, a doped silicone lattice. And what we see happening here is when our diode is forward biased and we have the movement of free charge carriers, the electrons will start moving and they will start recombining with holes all over the place wherever they are moving. And when this electron-hole recombination takes place, it is an exothermic process. As you know, exothermic means it releases energy. Now, in a silicone lattice or a germanium lattice, this energy is released as heat, which causes this crystal lattice to vibrate. So not much happens. All it does, it causes the crystal lattice to vibrate. And this type of a diode is called a direct band gap diode. So a silicone or a germanium diode that is forward biased obviously doesn't emit light because it doesn't have enough energy when the electron hole recombination takes place, and it's known as a direct band gap. Now, what if we were to change the silicone to some other element, such as gallium arsenide or gallium nitride? Well, students, that's the compound that we actually create our light-emitting diodes from. And they are known as indirect band gaps, simply because when the diode is forward biased and we see our electrons and holes start moving, an electron-hole pair recombination takes place. This energy that is released is high enough so that it is released as a photon. That's why you see I've drawn photons here in the lattice structure. So every time we have an electron-hole recombination, a photon pops out as energy, and this photon then is what you see as the light emitted by the diode. And this, students, is the circuit schematic of our light-emitting diode. Important points to remember: LEDs are not made from silicone and germanium because they have a direct band gap and they don't emit photons when we see electron-hole pair recombination. Light-emitting diodes are made from gallium arsenide and gallium nitride, and they work well as an indirect band gap because we see electron-hole pair recombination has enough energy released so that a photon is released, and that photon is the light emitted that you see. Moving on, students, to the Schottky barrier diode. So the Schottky barrier diode construction, from what we can see here, is it's not a PN type diode. It's simply an extrinsic N-type diode that is connected to a piece of metal. So the piece of metal is the anode of our diode, and the N-type region of the diode happens to be the cathode. And we can see the crystal lattice here. We've got some silicone, and it's heavily doped. Now, what this causes to happen at this junction between the N-type material and the metal is we know that there's a whole lot of majority carriers, which are free electrons in the N-type material, and there are very few electrons that are sitting within the metal. So because of this concentration gradient, yes, students, you know that there's going to be diffusion that takes place. So we start to see these majority carriers, which are free electrons, start shifting over from the N-type region into the metal. And what that does is it sets up a depletion region, as you can see here. So the free electrons that were at this point, they've now moved over into the metal. You can see the concentration of free electrons in the metal has gone up, and that has created a depletion region because it's depleted of any free charge carriers. And here we have some immobile positive ions in our depletion region. And because the depletion region has been set up, and we have a whole lot of electrons on this side of the metal, these electrons actually set up a wall, or a negatively charged wall. And this negatively charged wall has an attraction to the opposite positive immobile ions, which sets up an electric field within this depletion region. What's also happening is this negative wall that we see here is what prevents any further electrons from moving over into the metal region. Now, once that starts happening, students, we can connect a source to our Schottky barrier diode, and basically we are connecting the positive terminal of the battery to the anode and the negative terminal of the battery to the cathode. So yes, you can think of it as being forward biased. And what happens is all these free electrons that were bunched up in the metal, they start moving down and out and being attracted to the positive side of the battery. Now, because we have a movement of free electrons, that creates this current to be generated, which can then flow. And because we have this loss of electrons in the metal, our depletion region suddenly ceases to exist, because that negative wall that was created here, which prevented further free electrons from coming into the metal, is now disappeared. So what we see is more free electrons from the N-type side of the diode starts moving into the metal side of the diode. And that, students, is how a Schottky barrier diode works. And what this looks like on the characteristic curve is simply this. So the dashed lines represent a normal silicon PN junction diode, and the solid lines represents our Schottky barrier diode. So you'll notice immediately the Schottky barrier diode has a much lower on voltage, but also a much higher breakdown voltage. So it breaks down easier, but it also turns on much easier. And I would ask you students to go and look up some of the applications of the Schottky barrier diode for yourselves, just so that you can enrich this part of the lecture. Now finally, students, we're going to look at the Zener diode. Now we introduced the characteristic curve of the Zener diode when we looked at reverse breakdown in one of the previous lectures, and I went into a very long discussion trying to get you guys to wrap your heads around avalanche breakdown. Now, as you remember, avalanche breakdown takes place when you reverse bias a diode, and you reverse bias it to a point where the reverse bias voltage is less than the breakdown voltage, and that causes our avalanche process to then occur, and we have avalanche breakdown, which, if we don't have a current limiting resistor or current limiting circuit, that's going to destroy our diode. So it's a very bad idea to ever operate a normal diode in the reverse bias region. And I also showed you that the Zener diode is very different in that it is a very highly doped diode. And this high doping causes it to have a much higher breakdown voltage. As you can see here, the breakdown voltage on this characteristic curve is at around 5 volts. And that has our Zener breakdown effect here. Now the thing about a Zener diode is it is built to actually operate within the breakdown region. And the reason for that is if you look at this breakdown voltage, it stays steady at 5 volts, but the current can continue to increase. Now to me, students, that looks like a very nice regulated source. So our Zener diode can simply act as a 5 volt source, which will remain at 5 volts, but still allow some current to flow through. And that's really what the application of a Zener diode is, as you'll see in future lectures, is it's used to make voltage regulators. But now what does the Zener diode construction look like, and how does the Zener breakdown effect actually take place? So here we have a Zener diode constructed in the flesh, and it's heavily doped. That's why you see here at the PN junction I have a lot more of our carriers and our doping agents all junctioned up here at the PN junction. They bunched up, and of course that creates a concentration gradient between the two. Remember, this is the instant in time that the diode is created. There's a very big concentration gradient of majority carriers, which are free electrons in the N region, and minority carriers, which are holes in the P region. And because it's heavily doped, we have an N plus region and a P plus region, just to indicate that it's heavily doped. So because of our concentration gradient, these majority carriers are going to start to flow. Free electrons are going to move across the p-n junction. But students, immediately as our free electron moves across the p-n junction, because there's so many holes in this region, they're immediately going to recombine with them. And because that process takes place, the depletion region that is set up in a Zener diode is a very narrow depletion region. As we can see here, we have a very narrow depletion region, although the concentration of immobile ions is very high in this depletion region. And we know that because we have positive and negative ions, it's going to set up an electric field within this depletion region. And I've represented that electric field by Ez, Z for Zener, if you didn't already know. Now, let's actually operate our Zener diode now that you're familiar with its construction. So as mentioned, the Zener diode is operated in reverse bias condition. So the negative terminal of the battery is connected to the anode, and the positive terminal of the battery is connected to the cathode. And as you would recall that when you operate a diode in reverse bias condition, the electric field that was set up in the depletion region now gets much stronger because it gets summed with the electric field that is now created by our source. And that's represented here. So the Zener diode electric field plus the source's electric field can go all the way up to 300 kilovolts per centimeter. Now students, relatively to other electric fields, that's pretty big and pretty strong. Because we now have such a strong electric field within the depletion region of our Zener diode, this incredibly strong electric field actually rips out free charge carriers from the immovable ions within that depletion region. It breaks the covalent bonds that are present, and as you can see, we then have a whole lot of electron hole pairs being generated within this depletion region, and these free charge carriers then start moving. As you know, holes move in the same direction as the electric field, electrons in the opposite direction of the electric field, and that is how we then have our current, which flows for our Zener diode being operated in reverse bias condition. And now students, you probably, if you recall the avalanche effect, this is a very different effect compared to the Zener breakdown effect. The Zener breakdown effect takes place because we have an incredibly strong electric field which actually rips out rips out electrons from the valence band, creating electron hole pairs, and then these free charge carriers then move to generate the current. Whereas very quickly with the avalanche effect, the electric field would impart kinetic energy to our free electrons, as you would remember. And that kinetic energy that was imparted to the free electrons caused them to move and hit into covalent bonds within the crystal lattice, and they would then break those covalent bonds and cause more electron hole pairs to be generated, and those more electron hole pairs that were generated would also get a whole lot of kinetic energy into the free electrons, and those free electrons would just continue bombarding and breaking covalent bonds. Avalanche breakdown in a nutshell. Very different to Zener breakdown, which is a very strong electric field ripping out free charge carriers from our immobile ions within the depletion region of the Zener diode. And that, students, is the end of this lecture for different types of diodes. So students, to recap this lecture, we started off with the solar cell and photodiode. As you recall, the solar cell is used to generate a current using the photoelectric effect. The photodiode is a reverse bias diode that is used to actually detect light. The light emitting diode, students, we looked at the direct band gap and the indirect band gap. If you recall, direct band gap is one that has silicon in the crystal lattice, and when we have electron hole pair recombination, not enough energy is released as a photon, so you don't see any light. But if we replace that silicon with gallium nitride or gallium arsenide, then when we have electron hole pair recombination during forward biasing, We have energy released as a photon, which you actually see as the light emitted from the diode. We then looked at the Schottky barrier diode, which is not a p-type or p-n-type diode. It is an n-type extrinsic diode, which is connected to a piece of metal. The metal is the anode and the n-type region is the cathode. And what we saw with the Schottky barrier diode compared to a normal diode is it had a much lower on voltage and a much higher breakdown voltage compared to normal diodes. And finally, students, we went through the Zener diode. We looked at its construction and operation, and we looked at the Zener breakdown effect. And I took you through the avalanche breakdown effect very quickly. So students, if you are still struggling with any of the topics covered in this lecture, please refer to your textbook. And of course, I would appreciate any feedback, comments, or criticism. And I look forward to seeing you in the lecture enrichment session. Thank you.